All right, welcome back to our 3D Geometry and Vision seminar. Today, we're very happy to have Varol speaking. She's an assistant professor at École de Pointe Paris Tech, and previously was a postdoc at University of Oxford, working with Andrew Sisserman. And so she had a pretty amazing PhD at INRIA, which won the LS PhD award, and has been doing a lot of really cool work in terms of human body analysis and tracking in terms of motion and behavior, and also some pretty interesting analysis of sign language. So Gould will be speaking about 3D humans in action, and we also have a guest panelist, Gerard. So anybody who's watching on YouTube, please feel free to ask questions during the chat, and we'll discuss afterwards.
Thank you, Angela, and thank you for organizing and having me today. And well, while we see people more and more in 2D these days on Zoom, I'll be talking about 3D people. And a particular aspect of them I'd like to focus is their actions or their motions, because I find humans are as very complex objects with their articulations and their movement in 3D, and particularly their hands, the way they interact with the world and manipulate objects. So I'll just kind of divide this talk on some recent works I was involved in on human motion synthesis as the first part, and hopefully as much as time permits, the second part on hand object reconstruction from videos. But let's well, briefly motivate and start from the basics, and hopefully you agree that humans understanding people and humans in the visual content is important. So I'm not going to go through these motivations in so much in detail, but just to remind ourselves that the space of human motion is very rich and complex, and even subtle movements can drastically change the meaning of the motion. And as Angela said, I'm recently working on sign language where these things are also particularly important. So among many of the applications, I'm showing a few on the screen. As you see, several include human-computer interaction, assisted living, video indexing. And yeah, recently I've been working on sign language analysis, which is a real use case of detailed human motion understanding. And I hope really that there will be more and more research in this area. But you also have others like sports analysis of people on soccer field and self-driving cars, where you want to know what the pedestrians are doing on the street and so on. Well, I'd like to start with a very brief history before I talk about recent works, because I find it really helps putting things in perspective, but apologies to people who have seen this before in my talks. So I find this work from 1970s from Badler et al. Really interesting, where they were trying to kind of shape what we call action recognition today as defining motion verbs in English. So it's like event concept that corresponds to some motions and motion primitives such as lifts, rises, swims. And if you think about it in 2021, and we're still defining the action recognition similarly, so there's not a universal set of categories. We determine a different set of actions in each data set and only target those in different scenarios. And when you think about the capturing, it was like, if you imagine the concept of video, even to capture a small sequence into a computer was already challenging, so let alone processing it. And at the time, one of the successful motion estimation from a monocular video, like a couple of frames, shown here was from Pentland and Horowitz in the 1990s. And they had a body model, which they fit to optical flow estimation. So if you think today we have like similar types of solutions, which just that we have better body models and better estimators, more compute power and storage and so on. And one striking property of this literature at the time, when you group them into model-based, non-model-based, 2D versus 3D, is that there was lots of emphasis on 3D and volumetric based models to represent bodies, to analyze their motions. And several of them are cited here. Just a few of them that were the most popular at the time, focusing on 3D, like how to model 3D bodies, were looking at how to represent with primitive shapes, like cylinder spheres, to approximate the human body model. like from Marhog and O'Rourke in starting 1970s. And given the difficulty of the problem, the field has shifted back to 2D representations after like a few attempts at the time. So we saw more and more of these stick figures, pictorial structures, kind of primitives such as rectangles and lines and points in 2D, which we're still using today, like open pose key points as a proxy task for as an intermediate representation for many things, or like for fitting a model on 2D. Just because the estimates for 2D is still easier for the modern models like CNNs or deep models. But I think now it's past the time to really be focusing on 3D people, because well, we have very expressive human body models starting in 2000s and 2010 with simple body model, which is very widely used today, and even more progress as of now, which I don't show here, but thanks to these models, we have made significant progress of estimating these from images, particularly motion estimation, which got really had remarkable progress in the past few years compared to, I don't know, at the beginning of my PhD, where it was really not working at all. So you have image-based, like a few of the pioneering work, but quite a lot of them, more of them today, is human mesh recovery from Anju Kanazawa, and the later follow-ups on motion estimation from video. So this is image-based, and you can think of it as extension to time, and more recently WIBE, and more follow-ups 2021 now, that given a video estimates the parametric model of the human in it pretty reliably. So I mean, it's still noisy, but it's already very good as a start for things like actions that I'm going to be talking about today. Another progress which made at least like today's research possible was the progress in the size and the variability of motion capture, such as the AMAS collection of motion capture that unifies all sorts of different motion capture studios into one parametric simple model, for example. That makes it easy for us to get access to large sources of motions. Another direction which I myself have been involved in doing my PhD is using synthetic data sets to train these data-hungry models to get free labels. For example, you see serial data set here where you have pixel level segmentation and depth kind of annotation, which would be really tedious and difficult to get for manually annotating things. So this allowed us to train for several tasks such as segmentation, even 3D pose estimation, and optical flow, and a number of more tasks. But we use motion capture data for them, and which means they are lacking semantic action labels, because motion capture is typically quite unconstrained motion. So you just have people doing dances and more high-level events, not primitively labeled actions, at least until recently. So what we've done is that we just combined all these progress in another recent work that extends Surreal to Surreact, which stands for actions this time, to apply motion estimation from video, where we have real videos with annotations for semantic actions. So you kind of get a pseudo label for the 3D motion by applying motion estimation, which is not precise, but good enough, that allows us to create synthetic data with, for example, you see some actions from kinetics dataset, which is quite challenging, and you can still get reasonable movements that follow, like correspond to the semantics of the action. One very brief result of that work, which came clear, was that we don't have enough motions per action in our training set. And when we look at these even action recognition data sets where you have on the order of 200 sequences per action, the more, the better it gets. Both in this case, I'm showing a plot of real and synthetic plus real, which are two different models trained on the synthetic augmented version versus just the real, where you get some improvement from synthetic, but still some more experiments which highlighted that we need more of these motions per action, which kind of motivates this question of can we actually synthesize human motions? So given an action category, can we generate infinitely many of them and just sample from a random distribution? And if you look at the literature for generative models of human motions, I kind of group them into two, either the ones that, given the past, predicts the future. So this is almost dominated in the literature, or you have some motion synthesis from scratch, but they're just unconstrained synthesis. So you get a lot of walking and running, which are also dominated in the data sets. And we want to generate controllable sequences, ideally by just writing some text, for example, sit down and then walk and then wave your hand. But for now, an intermediate step is to kind of have this symbolic categorical action conditioning where you say, give me an action of the action type 1, action type 2. And if you have corresponding data, it should be possible to train with the progress of generative models these days. So with that, I'd like to introduce this recent work led by Matisse and co-supervised with Michael from MPI, some effort towards this goal of generating action condition motions. And in our case, we've used a VAE, and more details you can find on this webpage. So just to define the goal, an input is a categorical action such as this one, sidekick, and then you want to generate a short clip that represents the semantics of that. And again, to obtain training data for this, we just go back to the motion estimation methods, where you have RGB videos with labels of actions, but no real 3D annotations. So we estimate them with methods such as wipe, like the one I've shown, which is noisy, but it gives us paired data for labeled action and a short sequence. But just to note that these are still very toy kind of data sets where they're collected from a laboratory environment, one person, there's always the same chair. For example, this is an example from NTU dataset with 60 or 120 actions. All right, so here is kind of an overview of the whole method that we call ACTOR. So it stands for Action Condition Transformer VAE. Because it's a variational autoencoder VAE, we have this encoder part shown on the left and the decoder part on the right. And there are a few key ingredients of this, which actually made it work. One is that it's not autoregressive, as in a lot of the generative cases. So you don't have the previous frame given to go for the next frame, which we found, for which we found a lot of difficulties in training, actually. So in the end, we go for this fully sequence level embedding approach, where you just encode the whole motion into one vector and decode it as, so you just you didn't kind of determine how many frames you want to output. So this is in practice, in our case, it is about 100 frames, 60 frames, like a couple of seconds, and you generate the whole thing at once. So this is one property of this. Another one is that we have this transformer encoder, which is taking as input a sequence of motions. And in this case, it's a parametric model. So you have the pose parameters of simple body model, for example, for every frame. And at the end of the encoder, while you also have position encodings that are added to each of the frames, at the end of the encoder, you want to summarize them into a single vector. And what we did is kind of to follow this, for those who know, like VIT, Envision Transformers, or BERT, the class token that kind of summarizes the sequence into one embedding. We've used action-specific distribution parameter token, so mu and sigma, if we consider a Gaussian distribution in VAE, that allows us to take the corresponding embedding to summarize the sequence, and then kind of reparameterize it to sample a vector from it, the Z motion embedding space. And we also have to have the action conditioning at test time, at the generation time, which we also incorporate with an additive token term, which is learnable per action. That kind of shifts the space to another one for per action. And the conditioning, as I said, goes for the number of frames that you want. Simply what we did is to input positional embeddings, as many as we want to output as the input to the decoder. So in the end, you just get another sequence. So we have this reconstruction loss to train the autoencoder part. That's the other key ingredient for which we've followed the motion post-estimation literature actually by defining loss on not just rotation parameters, but also on the vertex positions, which turned out to be key to constrain the training. I'll just show some samples later. Okay, so this is kind of the general overview. Let me show some examples of input-output pairs. So for each action, which is written below, I'll just play a little video. Sorry if my internet is lagging or anything. You can find these also on the project webpage. So high knees running, knee lifting, left stretching, spinal stretching. Quite interesting categories. So these are the ones from the UESDC dataset, which have kind of like gym exercise like categories. And when we look at the diversity, of course, there are a few things you have to do to satisfy the conditioning, like standing toe touches. You have to go and touch your toes, but the irrelevant limbs you can move as you want, and that's why we have some of the diversity we expect. So if we play randomly sample 2 different motions, here you have a very slow one for the first one, 2 cycles for the second one. And if you look at some others, they all kind of start from a different position for their hands, and their speed is often different. So that we have some diversity within reasonable range. In this case, side kick, you can do with your left leg or right leg. So this is one diversity we got. And the hands, for example, they're irrelevant, so you can hold them in different places. That's what the model captures. All right, so some quantitative results, but no need to look at the whole table, is because especially it's getting a bit difficult to evaluate generative models. That's why we have multiple columns for, measuring different things, and that's why we're trying to aim for a like overall improvement on all metrics rather than only focusing on one. But some of the typical ones is FID, distribution, and distance to the training, to the test set. In our case, we have this interpretable metric, which is the accuracy. So can we have a motion action classification model that takes in model parameters and which is trained on the real data? Can we, what's the performance if we given the synthetically generated motion synthesis? And we get about 90% on 40 action categories of this data set, UESDC, and 13 actions, which is from NTU dataset, which is a little bit smaller. So we mostly draw conclusions from this bigger dataset, which had some difficulties of training. So the first thing we compare is this fully connected naive architecture, which inputs and outputs a fixed size sequence. So that's also one of the disadvantages, but in this case, it didn't even train well. It was pretty high. So the real row gives you an indicative number of what it should be like for the real motions. And the recurrent neural network version, which is autoregressive, was also not as good, although I would say it's still fine, the performance, but we got the best performance with this transformer, which is outputting the whole sequence at once, and just kind of ablated the different components I've mentioned. This action-dependent tokens, learnable tokens, they both gave us also some more performance. All right. This was the architecture. And if we look at the loss, as I mentioned, we use a combination of rotation parameters and the vertex coordinates. And here I'm just showing numerically that the combination helps over the individual, but I'll just show qualitatively to kind of convey the message that you cannot put the loss only on joints and expect the surface to be, unless like properly initialized at least, you cannot expect the surface to be properly rotated. You can have all kinds of weird rotations if you only optimize for joints, in which case you get a perfect reconstruction for this skeleton, although it looks like a monster when you forward show the vertex. And with rotations, we had some problems of training actually, where I'm now showing a motion, except you don't see it because it's not moving. This happened quite often in different configurations in training, that where we were outputting just a frozen person, which we're still investigating. So this is still not clear why this is happening in certain cases. But this is what happened if we put the loss only on rotations. And just to clarify, the rotations here, we represent them by the 6D continuous representation, and there's some ablation in the paper for different kinds. If we put on only on the vertices, it was fine overall. Just a few unrealistic deformations. For example, in this case, on the shoulder rotation, you have some unrealistic deformation, but what we found best was this combination of everything, both numerically and qualitatively working well. And if you need to compare to the state of the art, well, first of all, there's not much work on this area. So there was only this action to motion, which came out recently from Go et al., which was also reporting GAN-based methods. And action to motion is a GRU kind of recurrent-based method, so it's autoregressive. And we've seen significant improvement on both datasets, both numerically and again qualitatively. So they output joints, so they work with joint rotations, so they don't output the surface, but they have a fitting post-processing step where they can also output a simple, but it's computationally more expensive, of course. So if you look at their native, like their outputs from the neural network directly, they have this kind of jittery motions for the action to pick up frame by frame, and then we have a much more smooth and I would say more realistic generation. So this is for Sidekick. And the last one for Throw. All right, so this was kind of the key results of this work, but there are actually a few more details that matter as similar to most works. I encourage you to look at the paper if you're really like into reproducing things that we found were important, or how do you weight the reconstruction against the KL loss to kind of have a trade-off between realism and diversity. This was important. Rotation representation made a difference. Like, as I said, we used the 6D representation, which we found easier to train. In other cases, we also have this freezing problem. For example, number of layers, the more the better, what then saturates at a certain position. And the batch size was kind of, we found out by accident that also it matters. So we used like smaller batch size than what we can fit in the GPU RAM, which improved the performance also. One interesting outcome, which I really find interesting, is to be able to generate variable duration, because we kind of condition also on the number of frames we want, is what happens if you train with fixed duration and at test time generate with variable duration, because that's something we can do with this architecture. And in this plot, I'm showing on the left that case where we train with fixed duration of 60 frames. So you have the dashed lines that shows the training duration. And let's look at the accuracy, the blue curve, that measures the accuracy when you generate different durations, and it drops as you go further from the one it was trained on. And if you train with variable duration at training time and at generation time also generate of different sizes, in this case, we look at the range where we randomly pick at training between 60 and 100. We see much more robustness to action recognition accuracy, in this case, to variable lengths. And you see a quick drop in performance below a certain duration. That's partly because the action cannot be discriminated if you don't look at a long enough sequence. And also it was not trained for that. There is some kind of robustness to further durations than the one we've seen at training time. But one detail I'd like to mention here is that if we directly went for variable duration training, it didn't train. And again, another training difficulty. We had to first train with fixed size to get the warm up of the layers, and then fine tune by adding more positional embeddings, for example, to go beyond 60 to the architecture. And if you look at the qualitatively, what happens if you generate 40 frames, 60 frames, and 100 frames? There is this, of course, if it's too short, it's incomplete, so the person doesn't stand up from picking yet. And what we observed when we make it slower and slower, well, longer and longer, is that it's, of course, gonna have a full cycle to complete the action, so it's gonna get slower, but we observed that it's not linearly getting just stretching in time. There was somehow nonlinear slowing down where some people could stay down when picking up a bit longer to get up. And of course, some variations as you sample another vector around this. All right, so this is something nice we've trained. We can now generate motions for given actions. We've investigated whether we could use this in other domains. So can we actually use it in action recognition? And for that, we've shown it on 2 use cases. One is denoising. As I mentioned, the real motion that we get from for training is from real RGB videos. It's a motion estimate, so it's very noisy. And the nice thing is that if you encode this motion and decode this motion through our latent space with the action information, you get much more smooth sequences. So you can think of a use case where you have a motion capture setting where you know the action, it's very noisy what you capture, so you could denoise the motion. A second use case which we've investigated is whether we can augment the training data with the generated synthetic data. And this was rather not conclusive so much because there's, again, the domain gap between the real and synthetic where you have a very noisy sequence and a very smooth sequence at generation. That's how we explain it, where we train only with real, original 91%, and then we try to add generated and it wasn't getting so much better, except when in low data regime, again, if you reduce the proportion of real data, then you get more benefit of adding the synthetic. But what was interesting is that if you denoise the data, then you get quite perfect results. So this is, of course, not kind of a benchmark because we use the action information and to denoise them. So we already know the label, but it's still encouraging that the cleaner data you get, better performance. Well, one interesting thing is the question, what happens when you interpolate in this motion latent space, as in most generative models we try to show. And one thing was like, in this case, is the angle of throwing changes, but it's not just the angle of the arm, it's even the duration. Like the first one finishes the action a bit faster because it started with a smaller angle, and then the last one goes from a larger angle and finishes later. And there were like other variations where you could interpolate between a sitting person waving and a standing person waving. So the person would gradually move from sitting to standing. Another case where you have a waving with the left hand, a waving with the right hand, and gradually shifting between the two. Just to interpolate, interpret the results. And of course, we have lots of failures. One is due to the root translations. I haven't really mentioned about this so much, but we get this monocular estimate, which means the trajectory of the person in space, XYZ coordinate, is very unreliable because there's depth ambiguity. And the training data, the real data, just keeps moving from, especially in the depth dimension, keeps moving back and forth. So that we kind of clean up with this denoising, but still we have some cases where the generations also move. So ideally, we should combine real motion capture data sets that are reliable with these noisy ones to find a good trade-off. Another failure case is interpenetration. We didn't prevent collision or loss or anything. So you see, and in this case, the shape parameter is always 0, which you can change if you want to change the identity. But that means, yeah, we don't take into account anything on the surface. But that also happens in the motion estimates of real data. This freezing problem I mentioned, which became part of the training problem, also happens in fine-grained motion. So you have this real motion, which is circling the head, and the generated motion, which doesn't move at all. So we still don't capture the fine-grained moments, but there's I think there's an ambiguity where we should communicate, and we don't, to the computer, what is the noise and what is an actual fine-grained movement. So there's no way to separate the two at the moment. So this can be just noise for the model that is smoothed out. That prevents us from getting detailed motions. So just to wrap up this first part with a few take-home messages, we've argued for non-autoregressive approach. So the one where you embed the whole sequence into one embedding. And that's because we actually started with an autoregressive transformer, which didn't really work, and we had some troubles until we found this this architecture. And then even if noisy, we have these motion estimates that provide us good enough training data for action condition synthesis. And as a side product, we can denoise them. And I believe that the better the motion estimates will get, the better the synthesis will also get. And we've kind of used these parametric models that generates realistic motions by not just skeletons, but also having vertices on them. But as I mentioned, the limitation, the main limitation to me currently is the details. So you have this motion where the action is punching, but we don't really even close the hands. That's because the motion estimation is not detailed enough. So I think, yeah, now that there are more and more progress in this field, we can put together things and improve. But this is the full pipeline, which I think can be extended with more actions, more details, and more expressive body models, such as the ones that have hands, dynamic soft movements, even the face and the feet. And they're not even guaranteed to touch the floor at the moment, and no interaction with the environment. So there's lots of future work. But yeah, speaking of hands, that brings me to the next part of reconstruction hand motion in interaction with objects, so in manipulation scenes, only from RGB videos. So this is a project led by Jana and in INRIA with Ivan and Cordelia. So the goal is to reconstruct, given a short RGB clip, the surface of the hand and its articulation, keeping in mind the objects, and then also finding the rotation for the object. And a brief motivation is that we have, well, we use our hands for daily life activities, and beyond that, we have tasks that require high precision manipulation of objects. And if one day we want to teach a robot how to do these tasks, to automate them, we need to be able to automatically recover the precise hand and object in 3D, and not just with skeletons, but precise surface as an intermediate task. So that's why we kind of work on this task, which turns out very difficult. So I don't know how we're gonna transfer them to robots one day. So if you look at the literature, a few of the recent work only here, and more and more coming these days in CVPR 21. We've started in 2019 with a synthetic database approach, where you have lots of ground truth from synthetic renderings for estimating a parametric model of the hand and kind of a sphere transformation for the object at the time. And now people have also looked at 6 degrees of freedom object pose estimation, so just a rigid transformation to a known object category, and also skeletons or robotic hands. But mostly, most of the papers and works focus on a single hand. So although we manipulate mostly with 2 hands, that has been one limitation. Another limitation is that most of these work require fully supervised, annotated data, but getting annotations for this is really difficult. That means datasets, like models trained on a specific dataset, cannot generalize beyond that specific domain. So it's not something general purpose yet. That's what we were trying to address. And that's partly because of the datasets available. And it's not that there's not been efforts. There have been like tremendous effort to collect hand datasets with various properties. There have been the ones that use magnetic sensors, kind of motion capture, the ones that use multi-view cameras, depth cameras, semi-automatic annotations most of the time, but they are mostly limited in objects that are about 25 objects per dataset. And as I said, when you train on this kind of dataset, you cannot hope to generalize to anything on the wild. That's why, we kind of started thinking about moving beyond learning-based models in this work. And what inspired us is this recent work, FOSA, from ECCV 2020, that reconstructs, given a single image, human object reconstruction. So the human body and the object mesh is the ultimate goal, but it's quite similar to hand objects, except a few extra care you need to do. But that really inspired us. And with a quick overview of that work, you have an input image and some off-the-shelf learning-based models, but it's easy to get 2D bounding box annotation for those kind of models. So you can get a person detection. For each box of the person, you can estimate a 3D human body pose from an off-the-shelf model. You can, for the object, segment out the objects in the scene. And in this case, they also have a known object model, so they can fit with a differentiable renderer the known object model so that it fits best to this segmentation evidence. That gives them some good initialization, and with some priors on the some priors on joint fittings, such as the objects and the humans should be close to each other, they should touch each other, and so on. You can optimize to make it even better and spatial in the 3D depth ambiguity dimension. And it's already exciting, and that's what inspired us to extend this work to hand and object reconstruction without actually annotation of any sort. So except off-the-shelf models, we don't use any learning-based method. That means that's more generalizable across datasets, as long as the 2D segmentation, 2D box detection, those kind of things work. Yeah, so this is kind of the objective. So we don't want to use an annotation for 3D. We want to be able to generalize, hopefully beyond a few categories. So we want to be generic to categories. And with that, we have also aimed for increasingly challenging scenes and shown like two hands interactions on this Epic Kitchen dataset that is quite challenging. And kind of unknown objects, which means you have an approximate CAD model for those images, but you don't have the precise 3D. And in Nature 3D, which is annotated, you have everything. So which allows us to do quantitative analysis. Yeah, just a brief overview of the method. It's similar to FOSSA. We go for first the bounding box detection. And in this case, we do video, which I'll show that we have benefits from this temporal smoothness. So we detect and track bounding boxes for objects and hands. And this is possible thanks to a recent model trained on 100 days of hands dataset where they manually annotated hands and objects. So this gives us a 2D bounding box. For those regions, we have segmentation that are trained, for example, on COCO dataset. For the person pixels, we can take out the hand. We have kind of an object agnostic segmentation to get the object. So we have an initial fitting to these segments and a joint fitting, which takes into account the interaction. So they have to be close to each other. They should be touching to each other and avoid an interpenetration, those kind of interaction constraints. So just to summarize, those components we've used come from really recent work like CVPR 2020 for detection, Frank mocap for initializing each hand in 3D, which is trained on its own mix of hand datasets, and segmentation also for getting the masks. A few qualitative results of these masks when we track and segment on HO3D small scale but annotated dataset where we can evaluate their quality. They're not perfect, but they're reasonable to give us a start. So what we do for the object is with a differentiable rendering, which is occlusion aware, we find the best fit of the known object model to the segment and also account for temporal smoothness to make it better. But this is how it looks like if you independently initialize the hand on the object on a video, which is going from left to right. You see different frames of the video. And yeah, so they're not smooth, they're not even touching, they're not close in space when you independently fit and initialize the hand and the object. The next stage of our fitting, we only account for coarse interaction, what we call joint fitting with coarse interaction is with temporal smoothness. So we want the vertices that are nearby frames that are close to each other, and hand object interaction term, which is coarsely making sure that the centroid of the object is close to the centroid of the hand. So you kind of minimize this distance. So I'm just going to play a video of this optimization step where they're getting updated. So you see that they get similar across frames and also close to each other, the hand and the object. The next stage is the refinement, which is accounting for more fine-grained corrections, which you cannot really measure with these metrics that measure the hand object error, but we measure with other evaluation metrics. When we impose constraints on collision and contact, which means we don't want interpenetration of the hand and vertices getting into the object mesh. So that is avoiding collision to repulse them from each other. The other is contact. So we want the points of certain regions of the hand, for example, fingertips, that are close to the object to be touching. So we minimize the distance so that the object is not flying in the air, for example. So I'll just play another video of the optimization where I'm not even sure it will be visible, but you might see that visually the reconstructions get much better and more realistic by avoiding these contact constraints. All right, so some of the qualitative results where we see the camera viewpoint for this video and the rotated views. So you see it's a pretty short video, but when you compare it to the independent composition where you get all sorts of jitter, because the segmentation map can be noisy across time. So there are several reasons, but they're also far from each other. So that really helps both qualitatively and quantitatively. We have this, as I said, hand error, object error, which we see improvement by this joint fitting. So we just measure what if we don't have the coarse interaction, so the centroid getting closer. We have a very large error of 17 centimeters that goes down to 8. If we don't have this temporal smoothness, also we get a large error of 11. So those things help. And qualitatively, it's also visible that we kind of take out the fingers that are interpenetrating by doing this collision loss, and also get the fingertips closer by having this contact loss. But the improvements of these terms, we can only measure for evaluation metrics that care about interaction. So for hand and objects, they're roughly the same, they stay the same. And because these things happen within the small range of a centimeter, and if you remove the local interactions, so the contact and the collision. So if you don't avoid collision, you have a penetration depth of 10 millimeters. So this is going down with that. And here in this column, we are measuring the percentage of contact points. So this should be higher, the better. And if you have no contact, like you don't encourage contact, it gets to 72% and then gets to 77. So this is a good trade-off between the two. A couple of qualitative results with increasing difficulty I'm going to show. So initially HO3D, which is quite constrained, but still, if you look at the segmentation, there are errors that are happening quite drastically across time. But because of our smoothness term, even if we get it right in one of the frames, you can recover from it. So that in this case, the object is in a good state. But there are cases which we cannot recover from. So the object is initialized in a very wrong place. And also it's not even touching. So all of our constraints that encourage contact and hands and objects getting close to each other, it doesn't apply to this image. So it's another failure case. So the nice thing with this HO3 dataset, which is small but annotated, is that we can evaluate the quality of the errors, the source of the errors from multiple stages. So because we have ground truth masks, ground truth detections, we kind of do an oracle experiment of what is our lower bound for the error. If we had perfect ground truth masks, we could go down to 2 centimeters error on the object, for example, which is quite low. So the better these segmentation methods will get, the better the 3D estimate will also get. Similarly, if we have ground truth detections but are automatic segmentations, that's also a trade-off between the two. And currently we are around, that's 8 centimeters, which is still quite large. So this is kind of the data set of medium difficulty, where we have manually annotated the corresponding approximate CAD model for each video. In this case, the light bulb and a cell phone. And it's not too bad. So an interesting question is whether we can get these CAD models automatically by recovering it from like a ShapeNet kind of source of models. So here the segmentations are quite reasonable. Also, that allows us to get reliable 3D. A common error mode is because of the symmetries of the objects. So you can have these symmetric objects that are flipped, and that satisfy perfectly the segmentation term. So it's impossible to recover from this. So you have to really either have not segmentation map, but something like that is more depth aware, like a depth map, normal map, that you could use to solve this. But for now, with just the segmentation, it's not possible to recover. So the last kind of level of difficulty is epic kitchens. So we have this head-mounted camera on egocentric videos with all sorts of motion blur, resolution problems, and occlusions from all other objects in the scene. But the nice thing here is that we've shown that the method is generic to multiple hands, so you can just individually estimate that each hand and fit them jointly, which is, as far as I know, not so present in the literature. But as you can see, the segmentations are actually quite noisy. So we have this perception that segmentation works perfect because we see all these images on Coco, but it's far from perfect. That even causes drastic errors like this, where the bottle is segmented as a sink, but it's a very tiny part of the scene actually, which is in this blue region. Okay, so just to summarize this part, we've just investigated whether we can have a robust and generalizable model framework to recover hand object reconstructions without learning-based methods. And yeah, we can go beyond one hand to two hands. And if we have an approximate CAD model, that might be enough. But again, to highlight this limitation of known object model is really limiting the scale of the data sets we can work with, because we need a rough annotation for each object, and how to get this automatically from a gallery of objects. CAD models would be really an interesting direction that can scale this up to large data sets, where you can even use these pseudo labels, automatic annotations for training learning-based methods that go beyond a few hundred images and videos, which are typically used in this literature. And again, we have this perception of 2D detections working super well, but they're quite limited when you're trying to apply them to in the wild, which apparently is the main source of errors in our, like in this Oracle experiment. We've seen that if we have perfect 2D, then we get to a really, really low error on the 3D. Okay, with that, I'd like to thank for your attention and can take questions.
Thanks for the cool talk. So I think let's start maybe with a question from YouTube. What's your take on conditioning human motion prediction approaches like Actor on the environment of the actions performed in terms of the method and available data sets? Maybe an additional question on that. How could you extend this kind of approach to take into account interactions with the environment as well?
Yeah, actually, there is some very recent work that conditions on an environment, so the objects and the scene, in that case, unconstrained motions. So I think it would be interesting to combine both like having a chair and an action conditioning on sitting, whether this can resolve some of the ambiguities we have, like this flying people, and the context. I think there are also work on putting people in scenes from CU and others in MPI. I think putting all these together will at some point work, but it's very early to say anything, especially because we have limited data sets to put them together.
Mm-hmm. So I guess maybe in terms of the data, actually, so yeah. What do you think about pushing simulations further in order to generate more data, or do we need to look towards other constraints, maybe from more like these 2D constraints from all the 2D data that we have?
Yeah, I mean, I kind of took a break from the synthetic data because of the, I don't know, it seems you can, for the amount of synthetic data that you generate, maybe you annotate 10% of it on real data and you get better generalization. And the question is whether we can automatically annotate real data. If we can, I don't know, apply this motion estimation method, scene reconstruction method. I'm just making up all these methods that we have, apply them on hours of data, even if 10% of it is clean, that could be enough to train this, these models. I think we can cope with the noise at this level. That's what we have seen in this first part.
Mm-hmm. So
noisy and larger can be better than very clean but synthetic.
Mm-hmm. Just so out of curiosity, like the domain gap here between synthetic and real, is that because of also the gap between color images and observations, or is that more because of just like the clean motions and lack of noise?
Yeah, I meant more the appearance, but not in terms of, I mean, my insight is that the pixels themselves don't matter as much because we also have all sorts of augmentations on images these days. But the output space, like the things we can simulate in the simulation environment, are going to be limited to the objects and rooms we can simulate. And this is probably not capturing all the variability in the real data. This has been one source of problem with hand. I think in one of our early works on hand object reconstruction was also on synthetic. And we had this synthetic grasps, which were towards lots of over-grasping positions of the hands. So we never had I don't know, this kind of more natural, affordance aware synthetic data, which we could only get from real data. But yeah, maybe a bit of best of both worlds would be a good trade-off, a mixed training. Should I stop share, by the way, if you want to see each other?
That's up to you.
I will also see you better. Okay.
Yeah, so I'm just taking another look at the YouTube. I think there's another kind of related question, but maybe more towards your work on sign language. So
okay.
The question is, would synthetic data be good enough for sign language recognition and capturing details in hands and facial expressions, or maybe do you also end up with the same problems in terms of noise and diversity?
Yeah, I think the moment the detailed human motion estimation gets better, we can get there. But currently, I think even the best models won't be able to capture the complexity of sign language and like all these occlusions. It's getting even more complex with two-hand interaction and the motion blur that happens in very fast signing. I think, yeah, there's a lot of interest, and I get this question all the time, whether we can use synthetic data for sign language. It all relies on, well, all of you people who work on detailed hand and facial expression estimation, not only from image. So it's already difficult to get it from image, and then to get it from video. That will allow us to, maybe in a few years, but not now.
Mm-hmm. So even when there's like, in some sense, a bit more of a finite dictionary of like words and letters, I guess there's still a huge diversity in terms of expressiveness, in terms of like the individual.
Yeah, it's very combinatorial also. Like you have all the multiple channels of faces that determine the grammar, and the hand motion is the key. Sometimes the hand motion itself, where it starts and goes, is more important than the hand shape. So yeah, I think we need to wait a bit more progress on that first.
Mm-hmm. What do you think about like longer term motions then, like in terms of like these human body motion generations for like 100 frames, but then going again for another like 10 or 20 seconds or something like this? Can this be?
Yeah, I think this is like what we've been looking recently, and it's going to be the next step, because for now, one single action cannot last quite long. Like you can sit down in a few seconds and that's it. And the next question is, how can we transition between actions? So can we just have a sequence of these categorical actions, and how does that influence the transitions? And then once we have done that, can we just type some text that says slowly run towards this and then sit down? And yeah, the controllable, like more high level abstraction for controlling motions. But yeah, I think these are all exciting.
This would be really cool, I think, also
Yes.
from a content creation perspective, in terms of understanding sort of really this high level behavior in terms of what people are likely to do in the future in the space is quite probabilistic and diverse.
And in that sense, it's very similar to sign language production problem, where you have a sequence of signs which doesn't really translate to a full sentence. So you can initially go for synthesizing one sign at a time. You need to transition between them, which what we call co-articulation, as in speech. And then can we actually write a full sentence to produce the signing sentence? And that's, yeah, I think similar problems, just different types of data.
Mm-hmm. Cool. So maybe a couple of last questions then. I mean, how much do you think is currently limited by the expressivity in terms of fine-grained detail, in terms of, well, either hands or bodies or faces? Or do you think we can get by in terms of sort of general motion analysis with or perhaps even easier with a coarser approximation of the hand model or body model or face model?
Well, I mean, I would say we are still limited in terms of expressivity with these models. We can only get like the general semantics of like kicking with a leg, but yeah, as I showed, like all these punching and picking up, like you don't have the hands, and there we'll either have this motion estimation methods getting better, but another approach would be to capture them, like motion capture, to kind of have a mix of the two, real noisy but coarse kind of data plus detailed motion capture, clean but less maybe in terms of amount. Yeah, I think it would be really necessary to make them more realistic to get those details. I don't know if that answers your question.
Mm-hmm. Yeah, I think that makes sense. So there's another question here on YouTube. Can you expand on how the rotation representation was important in the training?
Yeah, I mean, we have, if you look on the paper, it's on arXiv, some appendix experiments where we've done axis angle, rotation matrix, quaternions, and the 60 rotations. And as far as I remember, in 2 of them, it wasn't even training, like this freezing problem. And then, yeah, well, one of them was maybe good enough, but yeah, it's just in terms of training, like the speed and the convergence, it was 60 was as important as any of the other parameters to make it work.
Yeah, rotations can be.
But yeah, maybe there's another bite size in this universe which we don't know of, and it's I don't know, this hyperparameter gets combinatorially increasing, and it's not clear what's the best combination.
Mm-hmm. So what do you think about also like capturing the texture and appearance of hands and bodies? Do you think this is more like a sequentially feed forward? You can get the geometric structures, and then you can get appearance and material properties and stuff, or can you get a bit of feedback from the others in some directions?
It's a good question. Yeah, to make it more realistic. But yeah, maybe JR can answer with this clothing models that will, if you can disentangle these things, such as we disentangle shape and pose at the moment, and if you disentangle all the appearance, you can probably just compose them. But maybe the difficulty would be to, like, if you're wearing a skirt, how to move this deform the garments a realistic way. Yeah, sounds more like a graphics. It requires more expertise on that side, and that I'm not really aware of. But yeah, that would be cool.
I guess Angela was also pointing at the fact that if you know the texture, then you can do a better job tracking, right? So you could basically not only to get a richer output, but to get a better tracking, basically.
Yeah, that's true. Like, just as we use segmentation for the second part, we could have used more detailed, like, pixel tracking and get correspondence to surface. I mean, I think there is some work in this direction, but yeah.
It was just, yeah, I was thinking along the lines of graphics, but also in terms of, you know, in graphics, it can be easier to represent, let's say, like a lot of the detail in texture rather than in geometry. And so maybe that's one way to get a bit more high frequency details that can help with tracking and these kinds of things.
Yeah, well, there are more and more of these, I don't know, conditioned, everybody dance now kind of direction, where what you're doing is only synthesizing pixels without going through a 3D model. So if that works, I think, yeah, there's a way to combine them, like a differentiably, for example.
Mm-hmm.
So I have a couple of questions, Angela, but I'm basically waiting. Maybe there's more on the YouTube channel.
No, go for it.
Yeah, I can. Yeah, thanks for the talk. Very interesting topics, and it's yeah, it's inspiring. I have several questions. So it was discussed a little bit, but do you think so? You've been arguing for predicting full sequences at once instead of having a recursive model. Do you think this will be like will scale to compositionable motion generation? Can you imagine like something where, I mean, some works in graphics, they actually predict batches of frames. So like basically I predict like 30 frames, but it's still a recursive model. And they've shown that that this stabilizes. So can you imagine like adapting your models in a similar way?
Yeah, definitely. I think at some point you need, I mean, this is kind of the primitive, the minimum unit we work with, like one action, but like if we want to go for these transitions between actions and generate longer sequences, we need either some hierarchical, like 1 second at a time model, and that also handles the transitions, or yeah, some master model that combines them and combines single units into, maybe the master model will be autoregressive, but the single units will be one at a time.
And so a related question is like, you basically now choose the actions, right? So how important is that the motions within each action are well clustered? I mean, some motions you showed like, well, you can move the right arm, left arm. There's some intra-class variance.
There's some, like, people are sitting and then standing while doing the same action, left, right side, but that's it, yeah.
But do you think that where does the model break? So if there's a lot of variability within an action, then does the model still work? Or you need actions to be relatively well clustered, basically?
Well, I think all it has to do is to determine which part of the body is important to identify the action. Like if it's my arm,
I was referring more to, for example, like if the distribution is very multimodal, that whether like your transform, like VIE plus transformer model can reproduce this variability within the class.
Well, yeah, there's, I guess, a limit of what you can do with the single Gaussian. Does it work? Angela, do you hear me, or is it just Gerard who froze?
Oh,
Okay,
I think
we lost
unfortunately we
him.
just lost him.
Okay, I'm not sure if he'll get this. I can maybe wait.
Yeah, fun times on internet connections.
Yeah. And with my short-term memory, I already forgot what the question was.
Oh, I think Sherrod is coming back.
Okay.
Yeah, sorry. I somehow like it froze. You guys were frozen on my screen. I couldn't hear your answer.
Okay, I already forgot the question actually.
Yeah, the question was about how well it can reproduce the variability within a class. So for example, you have many different ways of sitting on a chair or many different ways of picking an object. I mean, you could pick it with one hand, with two hands, with left hand. So how well does this model cope with these difficulties?
Well, in our case, it's hard to measure, but I guess this is a typical problem with VAE where you have a single Gaussian prior. So anything that encourages diversity and that can directly help here. But yeah, we haven't really observed. I think in USDC dataset you have lots of variation, and it was still, yeah, it's hard to measure how much of the diversity we capture. So there are some metrics, but it's not very interpretable. Yeah, I assume that we don't capture all the modes. That's
So
just
maybe a more detailed question, like you have, I think you mentioned you store the mean and variance per action, but at the same time during training, you still force the mean to go to 0 and the variance to go to 1, right? Or do you then?
So what we store is a learnable token that controls per action how to summarize the sequence, but then per sequence you have a different mu and sigma that you're trying to make it close to 0. Yeah.
I see, but I guess then there's kind of a trade-off because.
Yeah, if you can multiple mu's, like I don't know, I think you can hack it if you know how many modes you have and try to enforce it explicitly to have multiple modes by having multiple tokens. That could be an obvious way, though not very elegant, but yeah.
So one question about the constraints I mean, Angela was asking about this. If you have to condition on interactions with an object or a scene, I mean, that's the general problem is that the machine learning model is difficult to impose constraints at test time, right? So how do you think we should go about this? Like is it the representations that are the key, or do we need to think of optimizing at test time or integrating the optimization within learning, or what's the solution to this? What do you think?
I mean, if you're allowed to spend a bit of post-processing time, of course, the best is to do a bit of test time fitting, but if not, you just have to depend on the data, and I'm not sure if you have enough to represent all sorts of variability. And yeah, as you said, how to represent the whole scene into like a representation that you can feed in as input. And actions is easy. If it's 40 actions, you just have a one-hot encoding. But how to represent a whole scene mesh is to be investigated. It's really open.
So Angela, do you have more questions? I have one more question, but if you have one question, you can go ahead so that it's interchanging.
No, it's fine. I think it's pretty interesting in terms of the scene interactions and stuff. So what's your question?
So my question was about the hand tracking results. You impose interaction constraints, so you make that you avoid interpenetration, and you also make it snap to the object. But how do you know when the hand should be in interaction with the object and when not? So for example, like I'm grabbing this, right? But my finger could be like this, or I could even throw it up and down. And how do you know?
Yeah, I mean, this is very hacky. So we have like a threshold kind of almost a function which says if it's below certain distance, then it should be touching. But it's suboptimal, and we are not always touching everything. Like sometimes you're reaching towards the object, you're not even touching it. And I think we need at least a kind of a higher level even a classifier that tells, are we holding the objects? Are we reaching? Are we just holding and moving it? So there are a few categories we've identified actually, and it will be interesting to have a model that determines what state we're in, and then depending on that, you put more different types of constraints. But yeah, for now, I mean, it's not even with this approach of putting constraints with touching and repulsing, it doesn't, it's hard to it's hard to satisfy all the terms. So it never does it perfectly. As you said, it's at test time. It would be better to put it on simulation and just have a guarantee that you don't have any collision. But for now, it's just some soft loss term which encourages it, but it never gets to zero.
Are you using any priors, like sort of given the object, you have a prior on the pose or something like that?
No, I mean, the hand model is mono, so there's some kind of prior on the poses, but the object, I think there are recent works to get the affordances as prior, and that's going to be the future. I don't know. I think without that, it's really difficult to get how to hold a knife properly or a scissors.
I agree. Yeah. Cool. I think I have no further questions. Well, maybe one last question about accuracy. I didn't understand like how you measure accuracy of the generated motion. I have it here. So I didn't.
Well, yeah, I put that a bit in the. So there is a model which is trained for action classification given a fixed size sequence, and that's the one we use for FID. So to extract some features from the motion, and the one for accuracy, and even for diversity, everything we use that model. And the question is, how do you get that model? It's just chicken and egg.
Cool. Yeah. Thanks again.
Thanks for all the discussion also.
Yeah, thanks for a really cool talk. A lot of interesting future areas along those kinds of lines. Yeah, and then thanks, Gerard, for also very interesting panel discussion. All right, so I think we'll see you all next week for the next talk. And let me end the line.